Hello and welcome to the webinar. Today's topic is failure analysis of composite structures. We'll look at different types of problems you can solve today with MSC composite failure technology, and then we'll take a deeper dive into examples demonstrating how to apply this technology and how it works. Let's start out by looking at an example of an aerospace composite structure. I know this audience works on a wide range of flight vehicles, including aircraft structures, helicopters, spacecraft, missiles, and so on. But let's just pick one familiar example, an aircraft composite fuselage. Shown here is a CAD model of an aircraft composite fuselage. It demonstrates a few important features. It contains lightweight composite components, and these components are constructed from layered composite material, and they're bonded or fastened together. Let's take a closer look at the composite aircraft structure. You see here the skin is constructed from composite material. The stiffeners or the stringers are constructed from composite material as well. The stringers are bonded to the skin. Other components include a frame, shear clips, and tension clips. You might be thinking about the following questions at this point. Can MSC tools help me analyze the ply failure material in these components just mentioned? Do you guys offer a wide range of choice of failure criteria to choose from? Can your tools help me calculate failure indices and strength ratios? Can your tools take me beyond the first ply material failure and do progressive failure analysis? You might also be thinking, can MSC tools help me simulate delamination? How about, can your tools simulate crack initiation and crack propagation? The answer to all these questions is yes. Let's look at the first ply failure analysis. This is the ground level. This is a linear analysis based on failure theory. The user, in this case, chooses a failure theory, and Nastran will compute the failure index or strength ratio for the applied material for you based on your requirement. Our users also use this capability for optimization based on ply angles and thicknesses. The bottom line is, when you perform a first ply failure analysis, you want us to calculate failure indices for you. And based on that, you can identify that critical area in your structure. In this case, we're showing the skin stiffened panel, the stringers and skin. Identify that critical margin of safety, and then based on that, you can make a decision to sign off a part or reject it and redesign. But MSC offers additional technology to help you go beyond the first ply failure. One reason you may want to do that is maybe you want to evaluate the load redistribution in a composite structure after the first ply fails, and as the plies are failing progressively after that. Doing such analysis, you get to understand the ultimate load carrying capability of your structure. Here's an example of a composite fuselage skin under loading, and you can see the skin is undergoing progressive failure. This is an example we'll look at in more detail later. You may also want to simulate delamination growth from initial flaw or disbound. What is the residual strength as the delamination grows in my structure? And here's an example on the lower left-hand corner. You can see the skin is delaminating away from the stringer. This is another example. We'll take a more detailed look later. You may also want to study crack propagation in the structure, and maybe you want to find out, is the structure fail safe? Can my structure contain the crack growth within a stringer bay or a frame bay? Here's an image of a crack propagation through a stiffened panel. Again, an example we'll also take a look later. So in the next 20-25 minutes, we'll be looking at 5 different technologies offered by MSC. We can categorize them roughly in two categories. First one is Progressive Failure Analysis, PFA, and this is really looking at applied material failure. The other 4 methods we'll discuss fall under the category of delamination or crack propagation, and they are VCCT, CZM, breaking glue, and delamination. So let's get started and look at these different technologies. Before we go on, frequently asked questions from our users: what element types do you guys support? For composite failure modeling, what do you support? And we do support 1D elements, 2D elements, and 3D elements. But for today's presentation, let's focus on 2D and 3D, shell and solid elements. Let's look at a composite layup. We can capture this layer composite definition in shell elements. And in this case, typically the user is interested in the in-plane behavior of the plies. We're going to calculate ply stresses and ply strain. The primary interest is the in-plane behavior and maybe bending of the shell elements. In shell elements, we do have the capability to do progressive failure analysis as well. But in a structure, when your loading becomes 3-dimensional, when your load path starts to involve that 3rd dimension, or if the user wants to calculate stress and strain in the thickness direction, we have to go to solid elements. So we do support solid elements with a layer composite definition, and that requires our solid element to have multiple layers of integration points. And when we do that, we're able to calculate stress and strain at each ply simulated within a single solid element. And of course, we can also perform progressive failure analysis in the solid element. Another important element type is solid shell. When you take a solid element and try to bend it, it doesn't bend very well. It has its limitations based on its shape functions. So for solid elements under bending, we add additional assumed strain functions to it and make it a solid shell element. The solid shell element bends like a shell element. So it has the advantage of being able to bend better as a shell, like a shell element. I'll be showing you examples of using these 3 different types of elements in the next few examples. So let's first take a look at our first technology, progressive failure analysis. In progressive failure analysis, you, the user, select the failure criteria. And we have a very good selection to choose from. You can see here we have Puck, Hashing, Tsai Wu, max stress, max strain. So choose the failure criteria for doing the progressive failure analysis. In addition, we'll let you to choose up to 2 more failure criteria. So you can choose a total of 3, but the 2nd and 3rd failure criteria are used to calculate failure indices only. Only that first primary failure criterion will be used for progressive failure analysis. The plies will start to fail layer by layer. So when a ply starts to fail, what we do is we scale down the moduli, E and G. We make that failed ply very soft and effectively taking it out of the load path. And from that point on, the load can redistribute to other plies, and the load can also redistribute to the surrounding structure. Okay, we give you a number of choices to knock down these moduli. Another important feature is failed elements can be deactivated. So this is an important option. When all the plies within an element fails, you have the option to deactivate the element, take it totally out of the model. This animation here shows a pin bearing on a hole. And here we're using solid composite elements. And in this image, you're seeing the solid elements are failing internally ply by ply progressively. And also when an element completely fails, you can see we're deactivating it. So the elements actually would disappear from the model. Here's another example. This is an example of a shell model. It's a modeling a composite fuselage. And when the fuselage is under loading, you can see the damage starts out in the middle and it starts to spread progressively. And the colors you're seeing, red is the initiation of the damage, and yellow means the failure index has reached 1. So you can see the failure is progressively moving throughout the structure. And we're plotting the failure index of the outer ply only in this case. Here's another example. This time we're looking at a wing box. And you can see the damage starts out at the wing spar, and it spreads into the wing skin, and eventually it spreads into the entire wing box. Okay, so hopefully that gave you a good feel for how progressive failure analysis works and how you could apply it to your composite design. Here's an example. Thanks to our user for sharing this with us. This is a special approach using progressive failure analysis. We want to thank Victor Lee from Boeing for sharing this animation, and this is work he did on a NASA-sponsored project. And in this case, we're simulating crack propagation in a stitched panel. And what we want to do is we'll actually use progressive failure analysis with element deactivation to simulate a crack. You can see here in the picture here below, we have a stringer panel, stiffened panel, and there's initial saw cut across the middle, simulating the initial damage to the panel. As the structure is loaded longitudinally, you're going to see the crack emanating from the saw cut toward the stringers, and it's going to try to turn at the stringer, and eventually it's going to reach the frame. And eventually it's going to turn again following the frame, and under ultimate load, cracking the entire panel. So the animation I'm going to show you, you're going to see the crack initiating and propagating. But what you're actually seeing is we have a very fine mesh in front of the damage right here, and we're actually using progressive failure analysis to fail the elements. And as the elements are failing and deactivated, they appear and they actually are used to simulate the crack propagation. Okay, here you can see the crack is initiating from the saw cut, it's reaching the stiffener, and now it's turning. And it's actually bifurcating. It's turning both ways. And now the load continues. It continues to grow. And it's going to hit the frame along the flange. And eventually it turns and ultimately fails. Try it one more time. Again, what appears to be a cracked front is actually small composite elements being failed progressively and deactivated. Okay, that was a very good application of progressive failure analysis. Let's move on to delamination modeling. I mentioned earlier we have 4 methods here to present to you. The first is virtual crack closure technique, VCCT, and this is a fracture mechanics based method. The second method we'll present to you is cohesive zone model, and this one uses a special class of interface elements to simulate delamination. The next 2 methods are both stress-based. We're going to use a stress criterion. The first one is a breaking glue contact method, and the second one is a delamination method. Let's go ahead and take a look at VCCT. In linear fracture mechanics, a crack will start to grow when G is greater than GC. G is the strain energy release rate, and GC is the interlaminar fracture toughness. There are a number of ways to calculate the strain energy release rate. VCCT is one of the methods, and we have implemented this method in MSC software. Let's look at how VCCT works quickly. Here is a shell mesh, and you can see there is an existing crack in the model. And let's start loading up the structure. And as the crack tip is under loading, you can see internally at this grip point, there's a force F acting on this tip to keep it closed. Let's say this crack starts to open up, and it opens up with the vertical displacement of U, with the force F acting on it. We can calculate the energy release rate as F times U, okay, that's an energy term, divided by 2A, and A is the crack length. And instead of actually opening up the crack and calculate the displacement, we're using the crack opening just behind the crack right here. F times U. And this is actually a very slick method. We don't have to actually compute and open up the crack. We simply look behind it and use the existing crack opening. And this is a finite element approximation of VCCT. And that's why this is called a virtual crack closure technique. Okay, let's look at VCCT. VCCT is supported in both MARC and MD-Nastran. You will find the full capability of VCCT supported in MARC today. MD-Nastran has a subset of this capability. With each release, MARC capabilities are continually migrated into MD-Nastran. And what this means is today you can solve a lot of problems in MD-Nastran, but in some cases, when you need that extra horsepower, when you need a few extra options, you may have to go to MARC to find those. I will actually highlight a few of these cases later in the presentation. And this slide shows the different crack types supported. You can see we will support a line crack, we support shell face-to-face crack, solid face-to-face crack, a crack between a shell edge and a solid face, and crack between shell face and solid face. So pretty much all the modeling situations you have, we will cover with VCCT. Another question people often ask is, which modes of crack extension do you guys cover? Well, we cover all three. We cover the mode 1, opening. This is the interlaminar tension or opening mode. We also cover mode 2. Mode 2 is a sliding mode or an interlaminar shear mode. And mode 3 is a tearing mode or a scissoring mode. So you can specify mode 1, mode 2, mode 3, or all three, or any combination of them. VCCT will propagate the gap in a few different ways. The first way we do it is with a glued interface. In this method, the user knows ahead of time where the delamination is, and also where it's going. And knowing that, we can plan ahead and create one body and another, and we glue the two meshes together. And as the VCCT criterion is met, we'll start to unglue or opening up the glue joint. So in this example, you can see here we have a glue interface, and this region is not glued, simulating a crack. So VCCT requires two key ingredients. Number one, VCCT needs an initial crack. Second, VCCT requires the user to identify where the crack tip nodes are. So let's go ahead and run this analysis. And you can see here the crack or the delamination is occurring. And you can see this is a combined mode 1 and mode 2 behavior, because you can see the two parts opening up, that's mode 1. You can also see them shearing apart from each other, so that's mode 2. VCCT can also work by growing along element edges. So without knowing ahead of time where the crack is going, we'll let the program decide where it wants to go, and we'll start to split element edges automatically. And in this case, let's choose a criterion. It's going to go ahead and follow the max hoop stress as a growth direction. So if we have a very coarse quad mesh, in this case, you can see what happened. The crack really wants to kind of turn and go upward like this, but it only gets to crack along the element edges in this case. So this is the result we got. If we mesh this with a finer triangular mesh, and now you can see cracking along the element edge looks more like this. VCCT can also grow with remeshing. That's another capability. Let's look at that. And this is what it looks like after remeshing. So as the crack is growing, the program looks ahead of the crack tip, looks at the max hoop stress and determine which way it's going, and it continues to remesh in front of the crack tip. This way allowing the crack to very naturally grow in the direction it wants to. I'll show you an animation. This is an animation on the left-hand side. You notice we have a pretty fine mesh being remeshed as the crack is growing. And it's naturally allowing the crack to grow and curve upward. On the right-hand side, I turned down propagation along element edge, and it does have a different behavior. This is a good time to mention VCCT remeshing and grow along element edge is also only supported in MARC. Okay, this is a good example of what's currently not possible because of our user asked for it. We were able to put the enhancement into the program. Last year around this time, one of our users came and asked us, we have a stiffened panel and we want to have a crack initiating in the skin, but when the crack in the skin reaches the stiffener, does it go underneath the stiffener, or does it actually split the stiffener as well as it continues to propagate? So the user is asking the capability for the crack to bifurcate when it reaches a stiffener. Well, our current technology, we can't do that. So one of my colleagues came out with a great idea. He actually went ahead and introduced a crack front in the stiffener right here. So in this animation, what you're seeing is the crack in the skin propagates and it reaches the stiffener. It cracks the stiffener also because we have pre-planted a crack tip in the stiffener. Now, because of this request, our programmers got to work, and we're happy to report now we have this in our new technology coming in our next release. Our program now is smart enough to decide when it's required the crack tip is able to bifurcate. And I want to show you in this example. We're going to go ahead and load up this stiffened panel with stiffeners. Here is a lightning hole. We're going to let the crack initiate right here from the hole in the skin. I want to show you what happens when the crack reaches the stiffener. And just to show you, this is we actually stepped up the skin area, so you have multiple thickness in the skin, and the stiffener is glued to the skin. Let's look at the animation. That was pretty good. Let's try it one more time. So the crack is growing in the skin and it reaches the stiffener. The program made a decision to bifurcate and split the stiffener as well. Then it grows to the next one and decides, yes, the stiffener should also be split. So this is a pretty exciting technology coming in our next release. Okay, now let's switch gear a little bit. So far, we're looking at crack propagation along the edge of shell elements. Let's look at a very common example of delamination. It's happening along faces. In this example, this is a stringer and skin. So we want to study the delamination between these two components. In this example, we're using shell elements. So the stringer and the skin are modeled with shell elements, and we glue them together with our glue contact technology, except we are leaving this one region unglued, and this represents the initial delamination or the disc-bound area. So we're going to go ahead and push down on the skin and simulate the delamination. And here are the results. On the right-hand side, you can see we're showing an animation of the region released from glue. In other words, the delaminated area. So you're watching the delamination itself growing. We can look at differently on the left. On the left-hand side, we're showing you the glued region. So we're showing you as the delamination propagates what still remains as glued. Okay, so both are very useful visualization tools to help you understand the residual strength of the structure as well as how the delamination actually propagates. This is an example of solid elements. Again, you can see we're doing a face-to-face type of delamination, and these are solid elements. This is actually a very common benchmark problem called the DCB, double cantilever beam. For the guys doing delamination, there are several benchmark problems they typically will want to check out. DCB is one of them. I'll show you another one called the SLB, single leg beam. So in this example, this is a classic mode 1 behavior. You can see we're pulling these two legs apart, so it's a pure mode 1 opening mode. And here's a load deflection curve our customers would typically want to plot. You can watch how the structure behaves linearly up to a point and the delamination starts to occur. We have good post-processing tools to allow you to really study closely what's going on at the grid point level, how it's being delaminated. I'll show you one more example. This is the another benchmark single leg beam problem. You can see now when we push down in the middle here, it's a combined mode 1 and mode 2 behavior. Mode 1 because you can see there's an opening mode opening up the crack. It's mode 2 because there's also shearing going on. So combine mode 1 and mode 2. For these benchmark problems, our customers report good correlation between theoretical solutions and VCCT results using MD Nastran and MARC. One recent NASA paper showing such comparisons is shown here. One more example I want to show you. This is a delamination problem, and this time we're going to include some buckling behavior. In this problem, we're using again solid elements and simulating multiple plies, and we're embedding a circular defect. We're going to embed a penny-shaped flaw into the structure. So between two layers of solid elements, we're going to glue them together except the circular spot in the middle. So that's where the penny-shaped flaw is. And we're going to start loading up this skin panel in compression and see what happens. So the animation on the right shows you that penny-shaped flaw is growing laterally, and as that's happening, the overall skin panel is also buckling. So this is a nonlinear problem capturing not only the delamination but also buckling at the same time. And another question our users typically ask is, when you do such an analysis, can you also include material failure? And the answer is yes. In fact, as we do this analysis, we can also turn on progressive failure analysis. So we can also be tracking at the same time the plies. If they fail at all, we can capture that as well while the delamination is going on. It's important to visualize the crack tip direction, and this is a good tool where we can show you, we can plot the local X direction of the crack tips. Very intuitive, shows you physically how the delamination is propagating inside your model. Okay, so hopefully that was a good explanation on the VCCT, how it works, and how you might be able to apply it to your composite failure analysis problems. Let's look at the next technique, CZM, Cohesive Zone Modeling. Cohesive zone modeling is like VCCT. It's used to simulate delamination or crack growth. The big difference here is cohesive zone element is actually based on a library of special interface elements. So you can see image below, sandwiched between two sets of solid elements, is a set of interface elements. Let me go over very briefly how this material model works. These elements are special. We define these elements by looking at the tractions stresses on the top and bottom faces of this element. You can see here, these are the shear tractions and normal traction stresses, and that's on the vertical axis T here. So we map the traction stresses to the relative displacement between the top and bottom faces. So the relative displacement is plotted on the horizontal axis right here. So this is how we define the material model. The user may choose a bilinear model in this one right here. The bilinear model says, okay, go ahead and start to deform. The top and bottom faces can start to deform relative to each other while the traction stress goes up linearly. But up to the point where the user defines a critical relative displacement. When that point is reached, the damage starts to kick in, and this material starts to fail. And when you reach the final maximum relative displacement, the material modeled element is totally damaged. And the area underneath this curve is the cohesive energy or the critical energy release rate. And that's a quantity the user will supply. The user may also supply other models, for example, exponential model. Let's look at a CZM example. This is a published example where we're gluing two plates together with a layer adhesive. So we're going to load this up in single shear. And we are meshing both solids with TED10 elements. Notice the two different bodies have really different mesh densities, and they don't have to match up at all at the interface. And we have a layer of interface elements. Again, that does not have to match up with the two meshes either. And all three layers are glued together. Let's go ahead and load up the single shear joint. So if you watch the animation in the middle here, you'll notice the damage starts from the outer edges and they move toward the middle until it completely fails. Okay? And you can also watch the adhesive layer shown here on the lower left-hand corner here. When you see the color yellow, that means the cohesive zone element has completely failed. So here it goes. You can see yellow is progressing toward the middle until it totally fails the bonded interface. And let's look at the load deflection curve on the right. You can see here, as the structure is being loaded, it's going along linear and it's getting softer and softer and softer and finally fails. Okay, one important point to point out here is with CZM, you do not require an initial crack in the structure. Recall that the VCCT method, the user had to provide an initial crack in the model. So the advantage of the cohesive zone method is you don't need an initial crack to exist in your model. Okay, so that concludes the CZM discussion. I hope you probably have some ideas on how you might be able to apply the cohesive zone modeling to your existing modeling requirements. Let's look at the next one, breaking glue. This is one of my favorite because being a stress analyst, I think I'm most comfortable with a stress criteria. And you can see here what we're saying is we're going to look at a glued interface. So this method requires that you know where the delamination is going to occur. And we're going to have a glued interface. And we'll look at the glue interface and look at the interface stresses. We're going to look at the normal stress and tangential stress or shear stress. And the user will be supplying a normal stress allowable and a shear stress allowable. And we'll calculate the two ratios for you. And the user will also supply the exponents here. So for example, if you put in a 1 and a 1, we end up getting a linear interaction between the two terms. You can put in a 2 and a 2, and then you get a circular interaction. So when this term reaches 1, we have reached failure, and we'll start to release the glue contact. We'll start to unbutton the glue contact for you. Here's an example how you might apply this. I have a component and I have a layer, a coating bonded to it. So I have some suspicion my delamination will occur at that bonded interface. So I've glued these two components together, and let's go ahead and load it with a rigid body. So when the stress criterion is met anywhere along this glue interface, the glue joint is released, and the joint will fail. And it's important after the joint fails, we will continue to do contact analysis for you. So these parts can continue to contact each other even after the glue joint fails. Okay, so that was the breaking glue. One last method I want to present is delamination stress-based. This method actually uses the same stress criteria you saw earlier with breaking glue, but it's actually a lot more powerful. In the breaking glue method, you had to know ahead of time where the delamination will occur. You put a glue joint right there. In this delamination method, you don't have to know ahead of time where the crack is going to go. Wherever the stress criterion is met, anywhere in the mesh body will go ahead and split the elements for you. And this can happen between the two materials if you choose, or you can choose to have it actually split elements inside the same material. Both are possible. And here are just a couple examples. You can see these are really just each is integrally meshed body, but anywhere in the structure where the stress criterion is met, double nodes are created and the mesh are split, so the elements are pulled apart. There's also the additional option to insert interface elements where the mesh is split, and this combines the power of cohesive zone modeling with the stress-based mesh splitting technology. So let me demonstrate this with this example. So in this example you saw on the previous slide, this time whenever the stress criterion is met, we start to split elements. But as soon as we split elements, we start to insert cohesive interface elements into that interface. So in this animation, I have removed the upper half of the mesh to show you. So interface elements are inserted along the interface as delamination propagates automatically. So let's look at an example of delamination, and this is a very good problem for composite delamination. You can see here we have a composite plate, 8 plies, it's quasi-isotropic, symmetric. And in this case, we're going to use 8 layers of solid elements. And because we're going to push down in the middle here on this plate, we're going to see a lot of bending. So we've chosen to use solid shell elements. Okay, no double nodes. In other words, this is a single meshed body. Everything is congruent, nothing is pre-planted, and we're going to push down in the middle at a circular spot. And we're going to use the delamination criteria specifying a stress criterion. The next slide, I'm going to show you an animation of a quarter of the model. So we're going to use quarter symmetry and show you only a quarter of the model. Okay, so here you're seeing the plies are delaminated from each other, and the delamination is progressively moving through the structure. And what you're actually seeing is layers of solid elements are being split as the stress criterion is met, and that's simulating the delamination in this structure. And as soon as the delamination occurs, when the elements are split, they'll go back and do regular touching contact. In other words, they can continue to be pushed onto each other and do contact analysis after they're split from each other. And you have the option to specify automatically inserting the interface elements as the damage occurs. So this animation shows you as the delamination grows, we're inserting the interface elements automatically. Okay, so hopefully that gave you a good feel for the delamination stress-based method. So let's give you a quick summary of what we covered today. 5 different methods. First, we talked about progressive failure analysis, ply-by-ply failure analysis, and that works on shell elements as well as solid elements. Next, we cover VCCT, and that's a virtual crack closure technique. And if you recall, first we looked at the shell edge-to-edge splitting, crack propagation with VCCT. Then we looked at delamination between shell faces. And then we looked at an example of delamination between solid faces. We looked at cohesive zone modeling, where we use interface elements. And we mentioned the key here is this method does not require an initial crack to exist in your model. We looked at breaking glue contact, and this is a stress-based criterion. You supply the allowable shear stress and normal stress and the exponents for interacting, and will break the glue interface for you. And the last method was delamination. It's also stress-based, but now the crack will grow where it needs to, and the program will automatically split elements for you. Thank you very much, and that concludes our webinar today.